I start? All right. Yeah, so hello everyone. Thanks for coming. Today I want to tell you a bit more about our latest work, essentially on adding support for some form of parallelism into effect handlers that I'll motivate soon. This is, of course, joint work. Ningning, who's here. You can also ask her questions about the paper, Daniel Johnson, Dougal, Maclaurin, and myself. Okay, so I will not be trying to, we do not have too much time, so I'll not be trying to sell you about algebraic effects, but I want to run quickly through one example because I'll have more examples later on, and I want to make sure everyone's on the same page. So this is roughly the syntax. As you've seen with algebraic effects, we define handlers. In the handlers, we define the clauses that sort of determine how every operation is supposed to be handled. But then also every handler must implement a return clause which gets applied at the end. Once all of the operations are discharged, then the body evaluates into a value. This is the function that gets applied before the handler sort of is eliminated and is replaced by a value. And secondly, just for presentation here, I will be using stated handlers. So you can think of every handler as also having like an implicit state associated with it, and every single method in the handler will be taking this state sorry, as the first argument. So the operation clause takes the state, takes the argument to the operation, and takes a continuation that it can use to resume the program. And the return clause gets the final state of the handler and then the final value and can sort of modify it. So just to run quickly through this program, here we will handle this thunk here with the handler h that we've defined here that will define a simple accumulation effect. We initialize the state to 1. We begin running the body. We increment, as you can see, we perform ACC with 2. We handle it using this clause, which simply resumes the continuation with an state incremented by the argument, and with a unit, it doesn't really return anything meaningful. Either way, after this, we have an internal state of 3. After this perform, we have an internal state of 6. And finally, an expression hello. So at this point, we apply the return clause, which just pairs up the final hello with the final state. So the whole program evaluates to a pair of hello and a 6. Okay, with this example out of the way, let's finally get to motivation for our work. So, you know, at Google DeepMind, we have a ton of sort of massively parallel compute that we're doing, either for machine learning, large language models like you've seen today in the morning, but also other scientific computing, right? And our goal sort of from the infrastructure side is to make programming those huge parallel machines more accessible. And in particular, we do it, one of the methods that we apply is just basically through careful design of embedded languages, like the Python DSL JAX that, for example, my team is working on. And you know, pure functional programming is a great fit for this. Obviously, you know, those are mathematical functions. They're mostly pure. Purity is great for parallelism, but sometimes we want to allow programmers to introduce impurity just because, you know, it increases their productivity. And effect systems are a great way for us to actually manage this impurity somehow and sort of distinguish between pure expressions that can be parallelized and not. The only problem is that standard algebraic effect systems have sequential semantics. If you return to this example, the continuation here, right, it's delimited to the whole body. And so in particular, as we handle this operation here, it's really hard to say how the evaluation will proceed here. The continuation might be called once, twice, as many times as you want. It might never be called. So it's really hard to parallelize those programs because of those sequential dependencies introduced through those like widely scoped continuations. And it also turns out it doesn't have to be this way. We actually had a paper at ICFP describing an array language that we're working on. And it's an array, as I said, it's an array language, so this is an example program that just increments an array by 1. You can see this for expression, which builds another array, essentially by tabulating the expression that is here in its body. So you can see that we take as the input the array x, and we just increment every element by 1. And the DEX compiler is able to produce a parallel program for this, because obviously this expression is pure, so there are no dependencies between the evaluations. Interestingly enough, we can take a look at how DEX implements summing an array, right? Reduction with an associative function of an array is also a very well-known parallel program. But curiously, DEX actually uses effects for this, right? The way this works is that we enter a handler for what we call the accumulation effect in DEX. We don't use perform syntax, we actually use mutable references, and this plus equals operation that lets you increment the value of the reference. Very importantly, plus equals returns a unit, and there's no way for you to actually query the intermediate value of the accumulator. You only get the final value once the whole handler completes, kind of like in the first example that you saw at the very beginning. And even though this program is effectful, DEX can reason about algebraic properties of reductions expressed as effects, and is still able to generate a parallel program for a CPU or GPU from this little snippet, right? And so we have effects and we have parallelism. So there's clearly some possibility of combining those two things, but DEX only has essentially a fixed set of effects, and so then it's easy to reason about those things. But a natural question is, well, can we extend this, right? So we had 3 goals essentially for this work. One is we want to allow sort of more and varied effect signatures. We want to have an open system where the users can define their own operations. Secondly, we want to enable people who write handlers to actually decide how the sort of state and how the handler, the handler should be able to decide what to do around a parallel code region. And finally, the system should be compositional, right? The semantics of a program that uses, well, first of all, programs should be able to use multiple handlers. And second of all, the sort of semantics of the overall program should be derived from the semantics of the individual handlers, right? And hopefully in a sane way. And the key idea is actually really simple. The way we've done it is that we've said, okay, so just like every handler has to have this special return clause, what if we also force every handler to have yet another mandatory clause, which you can think of it as like a handler for the for expression, which is how we sort of introduce parallel subcomputation into our program, right? We will have a number of sort of similar expressions to evaluate, so, and hopefully those will be independent. So it gets a few arguments. The first one is the state as usual. Then it gets the number of parallel subcomputations that you'll have. Then it gets, as the final argument, the continuation, but only after the for. So in particular, not including sort of the body of the for. And then L is a little elaboration that we do, which is like an array of resumptions in some sense for every single iteration. So the way this works is that we take this for IE and we write this as an array of functions where each function takes sort of the state for that particular, in some sense, parallel subcomputation. It reinstates the handler in the body, and then it just, this is the expression with the index substituted for the index of that parallel subcomputation, right? And so you can see how we can use those functions to resume this. Yes, and yeah, and this handler reinstation happens automatically, right? The user actually does not control this. Okay, so just to continue the example of accumulation that we've been following, the return and ACC here are exactly as on the first slide. The only thing I've added is the traverse clause that you see here. So what happens? We take this array of resumptions and we basically, in parallel, because if this is the only effect, remember that L already has the handler in the body, so that would basically make the body pure. So this for expression can be evaluated in parallel. We evaluate all of the steps initializing their state to 0, because 0 is the neutral element of plus, which results in an array essentially of pairs of the individual results of the iterations and the sort of contributions they make to the total accumulation that sort of sums up the full program, right? Then we unzip the array of pairs into a pair of arrays. Obviously, that's a parallel operation as well. And then finally, we just resume the program after the for by incrementing the state with the sum of the updates and sort of the array of results. So, essentially with this pretty simple modification, we've been able to sort of express how DEX, roughly speaking, parallelizes the effect over those computations. Okay, I do not want to get too deep into the formal details in this talk. You have the paper for this. I just want to say that it doesn't really require too many modifications to the system, just to sort of calm you down. It doesn't throw the baby with the water. If those are the operational semantics for the basic sort of lambda calculus with effects that we use, those are the only extensions really that we add to make this thing work. Really, you only need to add the case that says if you have a for in a pure context and then a handler, then sort of the for, we look up the traverse clause in that handler and we use it to determine what happens around this for and then the details that describe how we form this array of functions. And then finally, this is just the evaluation step for the for. Once you actually have a for in a pure context, so the expressions in particular have to be pure as well or the program would get stuck, you can also just evaluate the individual expressions and replace it with the array. So nothing major happening there. Okay, so we have not specialized on any particular effect signature, so hopefully you believe me that this is extensible. You can have different operations. You have seen how traverse lets us define, sort of in each handler, decide how to handle parallel computation threads. So we're left with the third case, which is compositionality. So let's look at this, because this one's actually a little interesting, especially when multiple effects Yeah, well, obviously, multiple effects become involved. Okay, so let's look at the handler that we like to call weak exceptions. So if you've used sort of handlers for exceptions, the first two clauses will be familiar. Essentially, if you ever perform a fail, we completely ignore the continuation and just replace the whole result of the computation under the effect with the sort of empty value of the optional type that from Haskell we here call nothing. Otherwise, if you never call fail, the computation gets to the end and then return gets applied, which just wraps the final result in the sort of success case of the optional, right? But now what happens if we actually have a parallel region, the traverse clause, right? What we do here is, again, we just resume all of the steps, and again, if this would be the only effect you can imagine, this is a parallel for, or if there are more effects, it will also get handled, and hopefully the effect will also the other effects will also produce a parallel for. Which gives us an array of optionals. Then we use some functions here, again, borrowing from Haskell. We called it sequence to convert from an array of optionals into an optional array that's only defined if all of the elements were defined. You can also imagine this is a parallel program because that's roughly speaking, you can imagine it's a reduction on tags, right? You just check if all of them were defined. And finally, we say if there was any failure, then again, we don't use the continuation for the rest of the program. If all of them succeeded, we resume with, well, we don't use the state, but with the array of results where there are no optionals anymore. But it has quite, why do I call this a weak exception effect, right? And that's because it has interesting interactions around the parallel regions. Recall that sort of handling of one parallel thread cannot influence the computation that happens in other parallel threads. So if you have a computation like this, we just enter the two handlers, the accumulation that you saw before, and then weak exceptions. And then we just do 5 parallel steps, but the middle one of them will fail. The other steps that do not fail, they will just increment the accumulator with their sort of step identifier. And then after the for loop, also in the program, we just increment it with 1,000, right? If you executed this program with sequential semantics, the way this would go is you would enter this, the 0th iteration would just add 0 to the accumulator. The first one would add 1, and then the one with index 2 would fail. So the whole program would fail. You would expect to see nothing and 2 as the output, right? But under those parallel semantics, the way this happens is that actually all of the 5 computations in some sense begin running. And so all of them except for the one with index 2 get to the place where they increment the accumulator. So you end up with 0 plus 1 plus 3 plus 4 in the accumulator, which turns out to be 8. The second one fails. And then the traverse handler here realizes that actually there was a failure in the for, and so it doesn't call the continuation after the for. And so in particular, this perform doesn't happen, and as the result, you see nothing and 8, right? So in some sense, the sort of parallel combinator defines like a fork join thing in the semantics where we sort of diverge and make completely independent handlers in those threads, but then at some point we sort of join them and we decide how to combine the results and if we should actually continue running the whole program. Okay, just to finish off, I actually want to make there's a well-known connection between sort of algebraic effect systems and monads. While working on this, we're grappling with this question of, well, what is the relation of this between this and, for example, applicative functors? The accumulation sort of effect that I have here, that's actually one of the prime examples in the paper that introduces applicative functors. Sadly, it does not fully work out, and that's because, roughly speaking, of the sort of semantic differences that I described here. I should also say that this is not limited to the 4 expressions that you have here. You could also define this whole system using sort of a binary combination, sort of applicative style. And we also discussed the way to do it in the paper. We just used the 4 because that was kind of more natural for us in the context of DEX. The problem is that there are some applicative laws that connect applicatives and monads, and the parallel composition might not satisfy this, right? As you saw, if you perform 2 ops in sequence versus if you sort of, binarily split the program into 2 parallel operations, those 2 programs might not mean the same thing. But usually, if you just compose 2 programs with an applicative connective, then those 2, the applicative is a monad, then those 2 things should generally be equivalent. So there are some similarities, and in fact, for some effects, you could actually make this work, like for accumulation. But for example, in case of the exception effect, this does not always hold. So you kind of have to be a little careful. I would be curious if this can be resolved somehow. Yeah, I just want to finish by saying that I think there's something for everyone in the paper. So for those of you who are more theoretically inclined, we also add a type system to the paper, including all of the proofs of progress, preservation that you would expect. For those of you who are more practically inclined, we also have a Haskell implementation of multiple different handlers, including one that sort of draws those graphs that sort of lets you visualize the parallelism structure in your program. And there's also lots of examples, like random number generation that can be parallelized, ambiguity, it actually introduces parallelism into the program, which is interesting, and then also some sort of threading or shared state related examples as well. All right, that's all I have for today, and so yeah, thanks a lot.
We have time for questions.
Hi, Sam Lindley. Thanks for the nice talk.
Yeah, thanks.
Have you considered relaxing the restriction to pure functions in the for loops? It might be that you don't want to admit all effects, but there may be some benign effects that you could parallelize.
So you're saying do not allow all of the effects in for loops, just only the ones that are actually parallelizable?
Exactly.
Yeah, I mean, this system kind of does it, I guess, in a way, because as soon as you have a for, it actually requires the effect handler to implement traverse to say, what happens around the for. I think technically you might still be able to ask the for to be evaluated in parallel. Essentially, the way this works in DEX is that actually we just do like a type level analysis, and if the effects are parallelizable, we will do it. If not, then not. We could also decide to throw an error, but it would be like a little less user-friendly, I guess.
Okay, so you've not run into any instances where you wanted to be able to do something with effects that you couldn't do. It just kind of does the right thing in practice.
At least in that language, like for is a very fundamental sort of iteration concept as the way you process arrays, and sometimes you can't process them in parallel, right? So just like outright disallowing this is a little restrictive, which is why we haven't done it.
Okay, thanks.
Yeah.
Dominic Orchard, thanks for this lovely talk. So one thing I was wondering is whether for nested computations or nested for loops, whether you can do a sort of nested handlers approach to kind of recatch the inner traverse and change the semantics, for example, to switch from column major order to row major order to optimize the computations based on nesting.
You're saying that the handler would be able to sort of change the order of traversal in some sense?
Yeah, by kind of catching the inner traverse.
We haven't actually, technically, it might. I would have to think about it. It might be possible because you can play tricks like you actually don't have to call the array of sort of suspended iterations immediately. You can sort of delay it, thunk it, and sort of smartly. There are some funny examples in the paper where we do tricks like that. It doesn't seem obvious to me that you can do it, but it also doesn't seem immediately impossible to me.
Okay, thank you.
Yeah.
I'm afraid we have to stop here. Let's thank the speaker again.
Thank you.